Hello there. In this video we're going to continue our discussion on the properties of logarithms. In the last video we discussed four properties of logarithms that are extremely useful on timeless occasions. The first one being the log base a of some variable x plus the same logarithm base a of some variable y is equal to the logarithm base a of the product of the interiors. The second, the log base a of x minus the log base a of y is equal to the log base a of the quotient of a and y. The log base a of x to the power of y is equal to y times the log base a of just x. And you can rewrite any logarithm, say logarithm base x of y, to be equal to the quotient of natural logarithms, namely the natural log of y over the natural log of x. So in this video we're going to go through several examples on how to use these properties in various scenarios. Alright, so let's just start with some basic examples, especially ones that are associated with, say, rule 3. So if you have something like the log base 3 of x, and also log 4, you may not be comfortable working with logarithms that are not natural or, say, base 10. So we can use the last rule and rewrite this instead as the natural log of x over the natural log of 3. Keep in mind 1 over the natural log of 3 is just a constant, so we can call this c. So this is pretty much like c times the natural log of x, which is a very basic logarithmic expression. Similarly, if you have the logarithm of, say, radical expressions, for example, the square root, remember that square roots can be represented as fractional exponents. So this is the same thing as writing the log base 3 of x to the power 1/2. And then we can use rule 3 and bring this exponent of 1/2 down as a coefficient in front. And this is just equal to 1/2 times the log base 3 of x, right? And again, we can use that change of base formula if we don't like log base 3s. So we can rewrite this instead as 1/2 times natural log of x over the natural log of 3. And then we can bring this 2 up to the power of 3. And we can rewrite this instead as the natural log of x over the natural log of 3 squared, which is 9, right? Again, we can define c to be equal to 1 over the natural log of 9, because that's just a constant as far as we're concerned. So this is in very basic form, c times the natural log of x. Alright, so looking at the sum and difference rules, if we have something like the natural log of 8 minus the natural log of 4, now both of these do have irrational decimal representations, right? So subtracting irrational decimal representations can sometimes be annoying. So using rule 2, this is actually the same as the natural log of 8 divided by 4, which is the natural log of 2, right? So we have two irrational numbers subtracted from one another, and we get this other irrational number, natural log of 2, right? A little bit more easier to work with. Now I do want to make some important clarifications that I do often see people making. Firstly, the natural log of x plus the natural log of y in general is not equal to the natural log of x plus the natural log of y. In general, this is not true. Similarly, the natural log of x minus y, this is not equal to the natural log of x minus the natural log of y. The natural log of c times x, where c is some real number, it doesn't have to be positive, depends what x is. This is not equal to c times the natural log of x. That is, you can't factor out c's out of natural logs. Also, the natural log of x times y is not equal to the natural log of x times the natural log of y. That is also not true. And the natural log of x over y is not equal to the natural log of x over the natural log of y, right? So in general, none of these properties are true, so try not to make those simple mistakes. Okay, so let us look at a more involved example. Let's assume we have the log base 7 of 49 times x cubed, all divided by 5 times the 4th root of y. And let's expand this expression into a series of smaller, easier to work with logarithms. All right, so we have the log base 7 of something over something, so we know we can break that down into the subtraction of logarithms. So this is just the same thing as log base 7 of 49x cubed minus log base 7 of 5 times the 4th root of y. Now we have the natural log of a product, 49 times x cubed, 5 times the 4th root of y, so we can express them as a sum of natural or regular logarithms. Now keep in mind that there is a subtraction in front of this log, so that's going to distribute over that addition that we're going to decompose into. Right? So we have the log base 7 of 49 plus the log base 7 of x cubed minus the log base 7 of 5 minus the log base 7 of the 4th root of y. Alright, so remember that 49 is the same as 7 squared, so the log base 7 of 7 squared is just going to be equal to 2, right? And then we can bring this exponent down in front. So this is going to be 3 log base 7 of x. Log base 7 of 5, there's nothing special about that, so we can rewrite that as just log base 7 of 5. And then there's an exponent of 1/4 on this y, so we can bring that down in front, right? So this is going to be 1/4 log base 7 of y. And we can just rearrange this a little bit because that and that are both constants. So this is just going to be equal to 2 minus log base 7 of 5 plus 3 log base 7 of x minus 1/4 log base 7 of y, right? And that would be the expanded representation of what we started with. Now, also, it's sometimes useful to work backwards, take a long expanded expression and sort of compress it. So let's just work through an example to sort of see how that would go. So compressing, some people also call it condensing logarithmic expressions. So let's say we have 1/3 times the log base 4 of, let's say, 54 y to the power of 12 plus log base 4 of 3 minus 1/2 log base 4 of 9 y to the 6th. All right, so the first thing I'm going to do is I'm going to take these coefficients in front of the logs. This is 1, so that's not going to change anything. And bring them up. So that's going to give me the log base 4 of 54. So we have 54y to the 12th raised to the power 1/3 plus log base 4 of 3 minus log base 4 of 9y to the 6th to the 1/2. Okay, and we have logarithm of something plus logarithm of something minus the logarithm of something, so we can multiply the first two and divide by the second using properties 1 and 2, right? So we have the log base 4 of, so we have 3 times 54 to the 1/3, y 12th to the 1/3, all over 9 to the 1/2, and then we have y to the 6th to the 1/2, or the square root of y to the 6th. Okay, so what can we do with this cube root of 54 term, right? So remember that the cube root of 54 is the same as the cube root of 27 times 2. We know the cube root of 27 is 3, so we have 3 times the cube root of 2, right? So we have this is going to be equal to log base 4 of 3 times 3 cube roots of 2. And then when we have a power to a power, you can multiply. And this is an odd root, so we don't have any absolute values to introduce. So we're going to have y to the power of 4 there. The square root of 9 is just going to be equal to 3. And this piece we have to be a little bit careful of how we decompose this. So this is going to be y to the power of 3 to the 1/2, and then y to the power, let's see how do I want to do this. Well, one way you can sort of think about this term in the bottom is this is the same as the square root of y squared times the square root of y squared times the square root of y squared, right? Those are the same exact things, right? Because 2 plus 2 plus 2 is going to be equal to 6. And you'll see why I'm going to do that in a moment. Firstly, we have those 3's cancel, which is nice. And then we're going to have the log base 4 of 3 cube roots of 2 y to the power of 4, right? Now, remember, the square root of y squared is going to be the absolute value of y, right? Because we don't know necessarily if y is positive or negative in this case. And also, the absolute value of y times the absolute value of y is the same thing as the absolute value of y squared, which is actually the same thing as y squared, because the absolute value is always positive, and y squared is always positive also, right? So that's just y squared. So I have y squared times the absolute value of y there, right? So we can simplify those, which is nice. So this is going to be the log base 4 of 3 cube roots of 2 y squared over the absolute value of y. Since we do not know any restrictions on y, then that would be our final answer. But if y is greater than 0, it clearly can't be equal to 0, then this is going to be equal to the log base 4 of 3 cube roots of 2 y squared over y, because the absolute value of a positive is itself, and that's just going to be equal to the log base 4 of 3 cube roots of 2 times y, right? Very simple looking expression, right? So that's just some examples on how you can use the properties of logarithms to rewrite expressions, make things easier, make things more condensed, make things more expanded. There's several different instances where you would want one over the other. Hope you enjoyed.